So hello, this is the STOC25 video for the paper entitled Online Locality Meets Distributed Quantum Computing. And I am Augusto Modanese. I'm a postdoc currently at Aalto University, and this is joint work with many co-authors who are based all across Eurasia. And I'm going to talk about distributed quantum computing and how that connects with the centralized online model that is subject to a certain locality restriction. So in this paper we are connecting actually a bunch of models, so I'll introduce these step by step along with the results. So let's talk first about the basic models, of course. So if you're not familiar with the basics of distributed quantum computing. So one of the most fundamental models we have there is the local model, which goes back to lineal. And in this model, we imagine that every node in our input graph is actually a computer that has access to some unbounded computational resources. And moreover, every node is given a unique identifier with which it can distinguish itself from its neighbors or other nodes in the graph. And since we are doing distributed computing, our input graph and our communication graph are actually the same. So if your input graph is it's not only giving you your problem instance, it is actually defining how these computers are connected. So we also have synchronous, we just imagine we have some synchronous clock that is allowing these computers to communicate in some organized fashion, and they can send unbounded messages to each other in every communication round. So we don't have asynchronous issues here. So the basic complexity measure we are looking at in this model is then the number of communication rounds that we need to solve our problem. And basically, since we have these unbounded computational resources, you can imagine that every local model algorithm just operates like this. So every node just in t rounds receives messages from t hops away, gathering its radius t ball around it, and then it can compute some function on that ball and produce an output. So we are not charging in any way for local computation here, and the reasoning for that is that we just assume that communication is more expensive than doing local work, right? So if nodes are far apart, we can just imagine that the time scale for that, for just bringing the information from one point to another is going to take more than like just computing something locally. And well, that's a fair assumption to make, right? So this is the basic model where the nodes are deterministic, but of course we have extensions to that. So we can have, for instance, randomness access added to the nodes. So we can have nodes having access to their own randomness, local randomness. We can have some shared random string that is distributed all across the network. And we can also imagine that we are actually in some quantum distributed models. So we are like envisioning already applications such as the quantum internet that some people have in mind. We can replace the nodes with quantum computers and the communication links, the classical communication links with quantum channels. So nodes can send qubits back and forth, and then we get this quantum network. And similar to the distinguishing between private and shared randomness, you can also distinguish if the nodes have some prior entanglement or not. So it might be that we can prepare the state of our network by entangling some qubits between them, and then having access to our input graph, or the simpler model we just don't have that before. So you can see like how these models are all related in this diagram at the bottom of the slide, and there has been some recent work in separating all of these models. So so what kind of problems are we actually caring about here? So these problems that are the most studied problems in the context of the local model are called the locally checkable labeling problems. And this is a kind of search problem where we have our input graph and we want to produce certain labelings from a finite set that satisfy a certain set of constraints. And the constraints are simple enough that they can be checked by every node distributedly in some constant radius around it. So like checking the solution is something that is not expensive. And there's a broad class of problems that satisfy these definitions. So for instance, like the most fundamental, I would say, is the coloring problem. So just producing a proper coloring of your graph, given some set of finite colors, a finite set of colors. And we also have other interesting problems such as producing a maximal matching, producing a maximal independent set, which we often call MIS, or producing a sinkless orientation, so like orienting every edge in the graph so no node is sync. So given this, let's talk about our first main result, which is that we can get symmetry breaking for free in certain strong models. So symmetry breaking problems is a broad class of problems where we can all solve them in log star n in deterministic or randomized local. So if you're not familiar with the asymptotics of log star, this is something which is growing strictly faster than constant, but it's still much below log n. And so we know there is a kind of meta solution to all problems in this class. So you can imagine that we first break symmetry in our graph, so the nodes can compute some distance k coloring. This means a coloring of g to the power k of your graph for a certain fixed k that is constant and problem dependent. And then we use this coloring as some sort of anchor where to place our labels. So for instance, if you want to solve MIS, you can imagine that first we get access to this distance k coloring, and then we just start by augmenting our MIS. We first choose all nodes with color 1, then gradually we can start to increase this by nodes with color 2, if we can, if they don't have yet neighbors in the MIS, and then just proceed by these color classes. And if you have an MIS, you can also do something like a three color cycle. So you can just place 3s on the nodes of the MIS, and then every stretch between nodes where you have a 3, you can place a 2 coloring. And if it's an MIS, of course, these stretches are not going to be so large. And one thing to notice here is that finding this distance k coloring is the bottleneck. So this is going to take you log star n time, but the second one, like actually solving the problem when you have this, is only going to take you constant time. And you notice this in this quick algorithm I've sketched here for MIS, right? I mean, if k is constant, then you're going to proceed by color classes. This is going to take only time k. So and then one pertinent question is, like, for this class of problems, can we have also this log star n lower bound in stronger models such as quantum? And like, where is of course, if the model is strong enough, we're going to get that. And like, where is this threshold, like where we go from log star to constant? And this stronger model for which we would like to show this result is this actual super quantum model, which is called this bounded dependence model. So in this model, we assume we don't really assume we have an algorithm that we can like make sense of locally. We just assume there is some sort of random process that is producing a labeling of the whole graph. So this is a fully like stochastic view of an algorithm. And the only requirement we make on this process is that it satisfies this certain locality constraint here, which we call t-dependence. and this means there is some t dependent on n, such that if two components like blobs of nodes in our graph are far enough apart, then these whatever they produce, their output is going to be independently distributed. So here in the picture you see this A and B, and these are far apart, like greater than t, away from each other, and you can observe that the labels produced by the nodes there are independent from each other, like in the way you think of in probability theory. So of course we have this in randomized local, because there, if you just don't see your nodes more than t hops away, you're not going to be able to do anything about that. But actually, even quantum local has this property. So not quantum local with a shared entanglement, but the basic form of quantum local where we don't have a pre-paired entangled state. This satisfies this constraint. Because the laws, even though you are in quantum, you cannot violate the laws of physics and communicate faster than time allows you to do it. So this is why I'm calling this a super quantum model, because it is capturing quantum, but it might actually capture something that is stronger than quantum, right? And our main result, number one, is that you can, this model is strong enough that you can solve these symmetry breaking problems in constant time. So for free, basically, right? Since you already need the constant time even to verify your solution to your problem. So this is what this is saying. And this bounded dependence model for constant locality is also known as finitely dependent in some other contexts. And this whole process that we give here is even invariant under subgraph isomorphism, so you can think of it really as an algorithm, right? Even though it is like this abstract process, like you could think there is some reasonable explanation that you can perceive of it as an algorithm. So one corollary that we get here is that for every d that is greater than 2, you can have a finitely dependent coloring with d plus 1 colors in d regular trees. And this is interesting because this resolves a question that was posed by Coiteux-Roy in a publication that appeared last year. So well, yes, we solved this upward problem with this result, and for distributed computing in particular, and like these landscape of models I was talking about before, it is interesting to place this as an extension to the right there of the diagram we had before. And now we know that these symmetry breaking problems are easy in these extensions here to the right. You can see there is also this non-signaling local. You don't have to think too much about it. It's not very important for this presentation. But it's something that is encompassing both bounded dependence and quantum local with entanglement. And then we now know that in these models you can have these problems solved for free, but we have still this log star n lower bound on the left, and on the middle for quantum we don't know anything yet. And even though I'm saying we don't know anything, like this is important to see that this result has a consequence in that, like saying what kind of techniques we can use to solve this kind of issue here. So the easy way, like for certain quantum problems, we had it easy because we just proved the lower bound in bounded dependence or non-signaling local here, which is a stronger model. And then that carried over to quantum, right? And then we could show that you could have no quantum advantage in that case. But here you can see that quantum is sandwiched between two different complexity classes. So it could be either way, right? It could be that quantum ends up being having a log star lower bound here for this problem. It could be that it is actually constant in quantum. and we cannot use this bounded dependence model to say anything about it. And the attractiveness of bounded dependence is that, well, it is more amenable to graph theoretic techniques, right? I mean, just see it here from this slide before. We're just considering if certain regions are far enough apart and then they are independently distributed, and then we're just talking about probabilities, of course. We didn't have to touch anything related to quantum information theory or anything like that. But here, this is saying that any technique for settling like the complexity in quantum local is going to be it's going to have to talk about the inner workings of quantum, really. So yeah, so much about the first main result. Let's talk about the second one. So this is called sublogarithmic collapse for rooted trees. So what are rooted trees? These are trees where you have oriented every edge, so they are pointing towards the root. So you can see the root here is this node at the very far right. And we have all of these edges pointing towards it. And our main result number 2 is saying that, well, it's basically like a collapse or graph or gap result, I mean. So if you have a problem that is solvable with strictly faster than triple logarithmic locality in quantum local, then you can actually solve it in log star n in deterministic local. So you're just going to fall back to this class of symmetry breaking problems that we saw before in rooted trees, of course. And this result is actually not only holding for quantum local, you can actually replace it with this stronger bounded dependence model if you want, and you can even replace it with stronger centralized models, one that I'm going to introduce next here. So this new model that we introduced is actually called randomized online local, and it is a centralized online model, but I'm going to talk about it next. But this is the introduction of this model is useful here in that we can use this model to simulate bounded dependence with like no loss in locality. So in particular also things like quantum. And then we show that in rooted trees, if you are below this triple logarithmic locality in randomized online local, you can actually fall back to log star n locality in plain old deterministic local. And so basically you can see like this series of inclusions we have at the bottom, right? If you have this triple logarithmic locality in quantum local, you have no loss going to bounded dependence because that is a strictly stronger model. Then you just, from there, also without loss, you go to randomized online local, and then we have like this simulation result where we speed that up to log star n in deterministic local. So about this online local model, let's try and define it here. So first we have this deterministic online local of a couple of years back. This is, like I said, actually a centralized model. So you can imagine like an online algorithm that is processing your graph. We're revealing nodes each at a time, but the locality aspect is that when you are getting nodes revealed, you actually only get to see some local neighborhood around that node, right? I mean, you still have this global memory because you're a centralized algorithm, so you just like have access to everything you have processed so far, but this view you have is always a local view, and every time you see a new node, you have to commit to a solution to that node. So here I'm using like t equals 2 to depict what is going to happen to this, like during the computation of this algorithm. So let's say I reveal this node v1, and then you get to see its view, and now you have to commit to some label, some output label for that node, say color red, right? Then you get to see some other node v2 and its neighborhood, and then these are just like detached neighborhoods. You have no idea how they are connected in your graph, right? So you have to do something about this v2 and like color it with some color. And now you get a third node revealed, and then you see more, right? You might see that this V3 has intersecting neighborhoods with V1, V2, and now you've learned more about the structure. And now you have to commute to this V3, and let's say the algorithm picks a blue color, and then you reveal V4, and it picks a red color, and you keep on doing like this sequence of revealing nodes until you have revealed every node in your graph, and every node gets its label. So randomized online local is basically the same as this deterministic online local, but you have access to randomness, of course. And as I was saying before, there is someone who is revealing these vertices, and you can think of this as an adversary. And for the definition to make sense, this adversary should be oblivious of the randomness of your algorithm. Otherwise, like, this randomness is actually not helping you at all. And you can check the paper for certain details that we discussed there, like why does this hold. So this is the correct choice of an adversary, and we then show that you can simulate this kind of model if you have locality log n in rooted trees and going down to log star n. So in deterministic local, so we are not just removing this global memory component, but we're actually even de-randomizing this model. So you should compare this with some other results where we have like huge gaps between the two. So if you are, for example, 3 coloring grids, then in deterministic local we have a lower bound of root n, which is like very high, but in deterministic online local we have an algorithm with log n. So that's like an exponential gap between the two, and of course there's no way that deterministic local would simulate deterministic online local there, let alone randomized online local. But if you're in rooted trees, there is like a lot of techniques that you can use and do this kind of thing. So to summarize the talk, so we have these two main results. So in arbitrary graphs, we show that these symmetry breaking problems are actually solvable by finitely dependent distributions. And in rooted trees, I have this collapse or gap result here for log n from randomized online local all the way down to log star n in deterministic local. And we have introduced this randomized online local like class of algorithms. And there is follow-up work that is showing that this is actually strictly stronger than the deterministic for certain problems. You should check this iCal paper, which I'm also an author of. So this is still like leaving a little bit, like, even though this is a strong result, this is still leaving some regimes open. So if you are below the log n region, it might be that you could get some something where deterministic and randomized online local could be the same, but in general that's not going to happen. So there's still, of course, these open problems from this work. So like, what is the complexity of symmetry breaking in quantum? Is it constant? Is it log star? Is it actually something in between? That would be very strange, but could be true, right? And the second thing open is to extend this result that we showed for rooted trees to unrooted trees. And well, maybe extending, maybe it's not possible, right? But deciding if either is the case. So yeah, thanks for listening. Feel free to send me an email or anything if you have any questions about this presentation. To conclude, I'm just going to show the final references so you'll have them here on video. Yes, thank you.